morning, everyone. Probably listening to all the previous speakers, a lot of this seems to be very related. I'm going to talk about the NVMe FC part of it. So I work for Broadcom and just want to start with what we do at Broadcom. Basically, this is our data center portfolio. You'll recognize the Ethernet switches and fiber channel switches and LSI logic and Brocade and all those things. So then we have the fiber channel HBA. This is our total portfolio and our partners, and just a quick slide on it. So I'm going to talk about where the specification is and the roadmap, what NVMe functionality, what's new in the standard, what are the advantages, and we did some real good performance improvement where the latency is really low, comparable with Rocky for similar speeds, and the performance, the IOPs are really high. So just want to go over the techniques and the results of that. And my partner from VMware would cover VMware's angle on the fabrics, what they did, and where they are. So I believe all of you know this. I don't need to go over this. Just one line that this is the organization that creates the base standard, the fabric, and the management standard. And this is the roadmap. So basically, we are NVMe 1.4 is out. There is a couple of really cool features. There's a base spec that is being, coming out in the end of 2020 that merges with the fabric, and then the rest of it, management and the fabrics are all, some of them are in review. Many speakers before me have gone through this, so I'm not going to spend a lot of time on that. And this is something that has come out in the this year, 2019, 1.4, and has got this IO determinism. If you're working in the any kind of virtualization or even otherwise, that is kind of really good, along with the latency and where you can have predictable latency. And then fabrics and management side. So I'll just start on the basics with NVMe, FC functionality. So as you can see on the slide, this is just one host connecting to one target through a fabric. These are the top layers from the spec, like the host software is there, mostly in the kernel. Then it comes down, to the fabrics layer, and then goes down to the transport in the FC and the FC driver, actually. So these are the layers, and then ports the fabric, and the reverse happens on the target. And this is like one step, into the one more level down. So you can see on the target, we have a discovery controller. You would notice that it doesn't have any IO queues. Then we have the NVMe subsystem, which has got an admin queue and an IO queue, and there could be many controllers in a subsystem and many subsystems. So all these combinations are there. So I'm going to start off with how do we, connect. Basically, many of you who don't know about fiber channel, I was one of them. I come from the Ethernet side. So the first thing that it does is that it knows where the name server is. Like I used to work for 10 years in iSCSI. ISNS was a big pain. Everybody knows that. So here it knows there is a the well-defined address to which it can go and talk to the name server, get the name of the discovery controller, go make a login. The early stage, it will tell you whether discovery is supported or not. Then it gives you the addresses. It gives you the get log page will give you all the subsystems that it supports. Then you go and that is zoned also. So you go and log in, and then you establish the connection and start the IO. That is like the top level process. And this is from the fabric spec. This is not NVMe, FC specific. This is for every protocol. Basically, you do transport connect. Then once the connection is established, you start a connect command. This is generally where the IO queues are created. I'll go over this for fiber channel in the next slide. But then there is a authentication command and response and all those things, which is not mandatory. So for the NVMe FC, it starts with a create association. And here, this is where the admin queue is created. And if it is accepted, then you get an association identifier and a connection identifier. And then we start creating the IO queues. So IO queues, depending on the operating system or how it's configured, you can have an IO queue per socket, or you can have an IO queue per CPU. And depends on what the target supports. The target supports a lot of IOQs. You can create many IOQs. Depends on how efficiently you want to do it. Like if you have one per CPU, it is much more efficient because you don't have to have any kind of interaction between the caches. So this, when you come to doing a performance improvement, you'll see how important all this is. I have some slides on that. I'll talk about it at that time. So what is new, right? So this is something called IO determinism based on NVMe set. On the left, what you see is in the current state, where you have a big 4 terabyte NVMe disk, and all the carved into different namespaces, and the IOs are coming from the host. What you see on the right is basically it is split into different namespaces in the sense that you need support from the hardware for doing this. Like the CPU in the drive may be same, but it's able to do this. It's configured in a way or split. It's got enough DMA engines and all those things to support individual load. The whole idea is this: if you're doing like a virtual machine or something, you are kind of isolated. Somebody else doing garbage collection will not affect your workload. So this, along with predictable latency and endurance, gives you some level of control from your VM level. I think this really ties into that, into the next stage. And multipathing, and we know that earlier SCSI folks know about ALUA, asynchronous logic unit access, and this is basically very similar. Here we have, it could be a symmetric access like in the PCIe. What you see there, every path is kind of equal. But when it comes to fabrics, not all paths are equal. Some paths are more preference or optimized or whatever, and there must be a mechanism for the host to know. And that is where ANA comes in, and it kind of gives the information, which is the path to choose. Basically, there are multiple stages: optimized, inaccessible, which is evident, and change, which basically means that it is transitioning from one path to the other. All right, and the other one is sequence level recovery. Basically, in these days, if you look at Linux, it is about 60 seconds for an IO to timeout, and you don't want to wait that long. You want to handle it at the HPA level. You don't want the protocol level to come in and do that's like a big hammer approach. You want it to be done, the errors to be handled in the HBA itself. And how do you, people say in fiber channel there's no errors, but that is not right, because there could be some corruption somewhere, beta particles, whatever the reason. You want that handled at the lowest level possible without involving the host. And I think it's under 2 seconds. This is where the times out, and there's something called flush and read. Basically, that's how it queries what is the state of the command, and then informs, retransmit the packet, and takes care of it at the very low level. So then I want to talk a bit about the options that we have for fabrics. On the left is fiber channel, and in between you see InfiniBand. These are the only two that are not Ethernet based. The rest are Ethernet based. IORP has been there as a protocol for a long time. Implemented it in 2005-6 timeframe. Then came Rocky V2. Now that is adopted for NVMe. FCOE is being pushed by some folks, and then TCP is a new one that is there. So there's quite a bit of options on the Ethernet side. But I'll start to focus on the fiber channel. First thing I want to start is fiber channel is not RDMA based. But don't think that it is not DMA based, because a lot of people I talk to have a confusion. They believe fiber channel is capsule based, so there is no DMA. So even when you hear RDMA, the picture you get in mind is you have a server here with memory, and a server here with memory, and it magically moves. What really happens is the NIC or NIC has to DMA it, encapsulate it in UDP or UDP IP, Ethernet, ship it across, and then the reverse process has to happen. The same thing happens with fiber channel and has been for decades. So you do the DMA, the performance improvement, or the CPU utilization comes down because of DMA, not RDMA. So the ability to move that has already been there. It's lossless. Folks who work on fiber channel know better than me. And there is wide vendor support. So basically, interoperability is very well tested. People are very, very paranoid about it. in the fiber channel world, and they have this Interop lab running every once in 6 months, I think. So if you look at, we have this HBAs from MLX and QLogic, and switches from Broadcom and Cisco, and they're pretty well tested. And this is the Interop slide. This is from a talk like last October. So you can see a whole lot of NVMe targets are already there for Interop, and many more have come out in the last 1 year, gone GA. So you'll see the switches, the HBAs, everybody has been tested, and the whole ecosystem is and has been ready. Many of the targets are in the third GA. The fourth one may be working on, but the third GA for NVMe FC. So the commercial targets I'm talking about. So I'll switch to the performance improvement techniques, because to get to this level of like millions of IOPs from one HBA and less than 10 microsecond latency, there's a lot of stuff that we had to do. I will start with a standard 2-processor architecture. This is a very simple top-level diagram. You can see the DDR is tied to a processor. There are 6 lanes now. The root complex is inside the processor, which is a socket node. I could be interchangeably using those words. And the HBAs are connected. And there is a UPI bus, the ultrapath interconnect, which replaces the QPI, which connects these processors. And if there are many more sockets, this is how it's connected. But one thing I wanted to notice is the HBA. So in a server, depends on where you connect your HBA, unless there's a PCI switch, which most of the standard servers don't. Depending on where you put in your HBA, it will be connected to one processor. And if it has to access the other one, it has to go through an interconnect. And it depends on the slot you choose, right? So this is kind of interesting here. I'll go into one processor. Basically, this is like, again, a top-level picture. You have a separate L1I and L1D. Then there is L2. These are the caches. There is one unit, and there is L3 and root complex and all those things. I want to focus on the one core. I think since Nehalem, the L1I was 32 KB and L1D was 32, and L2 was 256K. L3 was 8 megabytes and above. But focusing on just that one unit, I think Intel recently has bumped it up to 1 MB, the L2, and L1D I think is now 48K. So this is really important when you are talking about performance, because you want to hit the L1 cache if possible. If you don't hit L1, your performance keeps coming down. Just look at the clocks, right? It takes 4 clocks only to access the L1, approximately. This is all, again, depending on your processor, it could be slightly up and down. 12 to L2, 40 clocks to L3, and about 400 clocks to DDR. So if you really want to hit 5 million IOPs or more, get like less than 10 microsecond latency, you want to make sure you get your data in the L1 cache. If it doesn't happen, at least the L2. This is important, otherwise you're not getting any of these numbers. So maybe I'll go to the next slide. Just keep that picture in mind, because when you send down an I/O, there is a lot of control structure associated with from all the layers. I cannot talk about ESX, but I can talk about in the block layer. In the Linux side, from the block, if you look in the I/O path all the way down, there is a lot of control structures associated with every I/O, which you need to access when the I/O comes back. Now, if you go back to the previous picture, you not only have to hit an L1, but you have to hit on the same CPU. If it is on L1 of another processor, then you're trying to pull it across the UPI bus, that means you don't have any more latency or performance. So one of the things that we did here is that, we are assuming this is the worst case scenario, the middle one, which is 1 interrupt vector per socket. So if at all you don't get enough MSIX vectors, at least you tie 1 per socket. And if possible, always have 1 per CPU, right? So the idea is that when an I/O comes down, we tag it and tell our ASIC, send it back on this particular MSIX vector, so that it comes when the I/O is completed. You don't have to go and grab the cache from the other processor or other CPU even. You want to go and hit the same L1, if not possible, at least the L2, right? L2 is like, as you will remember, is only 12 clocks away. So this is something we did. Of course, when I go into the techniques, I want to tell you I only picked 3. there are many, many, many more, right? I just picked 3 that gives you bang for the buck. The other is adaptive resources. If you are working on anything that has got to do with hardware, you will find that there will be some resources that are constrained, right? So either you can have one whole pool of it, put a lock on it, and then grab it. Then again, you go back to the previous scenario. When you take a lock, you have to make sure nobody else has it. The RFO, request for ownership, goes around across to all the sockets, which obviously means you kill the performance. So the other option is to take these pools and divide it up individually to each CPU. Now, you don't have control over the CPU in which an I/O comes. That's an application, or that's a VM deciding it. If you split it up, even if you have 16,000 resources, you split it up across 64 or 128, you get 1,000 or less than 1,000 resources. And if all the I/O is coming on a couple of VMs, then you just wasted it, right? It's not being used. So what we did was we created a pool where we create a small number for the local core, and then you have a public pool, right? So as the IOs are moving around, what we notice is it's not coming parallelly in all the CPUs. It will come to a couple of CPUs, then it slowly move to some as the scheduler moves it around. We will pull in from the global pool within the same socket, if it is all in the same socket. Otherwise, we'll pull from the other one, and then fill our, and this happens in microseconds. So you always have enough resources to use in the same core. And as it moves around, this gets, as the CPU, the load gets moved to a different CPU, this also gets moved around, except for the private pool. The other is interrupts. This is more of a religious topic for some of them, some folks. There's interrupt folks, and then there is polling, and obviously there is a problem there. Interrupt folks like interrupt because you get low latency. Polling is even lower because it's just spinning on it. But then again, it is spinning on it, it's consuming CPU. So, and of course, there are, Christoph was talking yesterday about the hybrid mode and all that stuff. But I don't know whether it will work in every use case, right? You could have in a data center a wild combination of targets, some of them very fast, some of them very slow. How it plays out, we don't know. Because it's not going to be the target or the number of controllers. CPUs are limited. Same CPU could be connected to a really fast controller as well as a really slow one. How do you make it work, right? So what we have done is we use interrupt to get started, right? And then you put it into you don't do any real processing in the interrupt other than fire a scheduler for the CQ processing. But what we do in the CQ is, as long as we have enough IOs, we kind of reschedule it internally, right? And what happens is, if there's not enough, then you'll go back to interrupt mode. Then we don't care. There's not enough IOs load, then interrupt is okay. But when there are really millions of IOPs, you always remain in the CQ mode. Be a good citizen. Don't process too much. Don't hog the CPU. But other than that, I have seen this go on for seconds without an interrupt. If there is an IO coming in, it goes in interrupt mode, triggers the CQ, then it goes on in a loop. If you have enough IOs to feed the CPU, then there's no reason to go back into an interrupt mode. So the beauty is, as the load goes up, the interrupts go down. And you all know in a virtualized scenario how bad interrupts are. So you want to cut it out. So I'll go into the performance results. So again, I just want to tell you the target is not a commercial target, because most of the commercial targets have still use the backend as SCSI or something. There are other people coming out on that, but this was done about 8 months ago. And so we used, I think it was a SLES or REL, I don't remember, target that is inbox. And these are the numbers that you get on the Gen 7 with 32 gig. So you can see that the gray one is the dual port. It far exceeds 5 million IOPs. One thing that is not shown here is the latency. The latency from FIO all the way to the target is under 10 microseconds. Again, this is fiber channel, in case people are looking at it from a different angle. This is fiber channel, FC-NVMe numbers. So this is a test done by NetApp a while ago, and you can see that the latency is even the IOPS, right? It kind of the hits that it's a wall at some point, but for FC-NVMe, it is much later. You can see that it's 0.56 milliseconds. This is an old one. I just wanted to keep it to show you that one. All right. So this is a test that we done with Microsoft. The blue one is the FCP, and the orange one is the the new. Again, this is on Gen 6. It's not even the latest chip. And Oracle, yeah. So the black one is FC, and the NVMe or FC is on the blue one. So you can see there is a huge difference between the NVMe and even the FC. And I'm not even comparing it with the older, before the performance improvement was done with older versions. This is just the latest versions of Fiber Channel. And this is just a comparison between SCSI FCP and NVMe FC. So that's all I have. I think I'll hand it over to Shobi. Shobi leads the development team at VMware. He's responsible for pretty much all TCP to, Rocky to Fiber Channel and all those things. We are working with them.
Do you want to take any questions?
Is there any question, or we can take it together at the end?
Sure.
Yeah.
All right. Thank you, Jay. Let me make sure I get accustomed to the environment, the screens here. All right, good morning. It's great to be here with you all. My name is Shobi Cherian, and if you came here with looking at the printed pamphlet, it says I'm from Broadcom, but I'm from VMware. I've been with VMware for over 14 years, and I've been working in the ESXVM kernel team, enabling the various IO technologies. So Jay and I go back a while. So he mentioned he's been working on the iSCSI enablement, so we had a chance to work together on enabling the hardware iSCSI drivers for ESX at one point. That was many years ago. And so when he called me up, this is around the time when the NVMe fabric spec came out. He called me up and said, "Hey, Shobi, there's something cool about this NVMe fabrics." And this was especially around the time that the FC part of the addendum was added. He was all excited. Ever since then, he's been a great proponent and a pusher for NVMe fabrics over Fiber Channel, and he's been a great partner. And I want to acknowledge and thank you for being such a good partner with ESX and coming along in the enablement journey that we have been under, trying to enable NVMe fabrics in ESX vSphere. So standard disclaimers, this presentation is still work in progress. Things, whatever I show here could change by the time the product comes out, with the standard boiler template. All right, the agenda. I'd like to introduce the NVMe next-gen stack that we are developing in ESX. This was, like I mentioned, mainly to adopt to the NVMe fabrics requirements. The advantages of going to this new model, I'll walk you through the benefits that we realized. I'll walk you through the I/O path, the data path, the interop that we have with our legacy SCSI-based stack, as well as the next-gen NVMe-based stack, and how to manage and control the NVMe devices in ESX. And last but not the least, I'd like to actually go and look into some of the cool proof of concepts that we have been able to do once we were able to enable the NVMe fabrics underneath. All right, so this is it. I mean, NVMe fabrics has arrived with a boom. There's so many choices, so many transports. Customer has a lot to choose from, and we are also seeing that there'll be ecosystems that build around these transports. There'll be customers who have existing deployments, maybe with Fiber Channel will gravitate towards Fiber Channel fabrics approach. There will be folks with RDMA infrastructure or TCP. So there are a bunch of choices that's in front of the customers. And our hope in VMware is to be able to provide all those choices, make all those choices available to customers, whichever they want. So this was our traditional stack. We've had NVMe PCI driver. It was a FAT driver, pretty complex. You can see all the logic that it had to do inside the driver itself, from doing the NVMe to SCSI translation, controller configuration, discovery, etc. But this was a fat driver. It served, and we actually released it back in vSphere 6.0, which was actually, I don't even know when it was, many years ago. But obviously the advent of NVMe fabrics changed the need, and we had to change this model. So this on the right side presents the new layered model that we have moved to, that we are moving to. It's introducing a new common layer, NVMe common layer, which can support, which basically supports all the new base specifications from NVMe. We also have the layer for fabrics, under which we can layer in all the various transport drivers and stacks. One of the other things that we have done is provided a rich interface of management, configuration, CLI based and both UI based as well. So this is the model we are moving towards. And in the next slide, I'd like to cover some of the advantages that this model is bringing to us. Since we have this new NVMe common layer, we are able to adapt to the latest NVMe base specifications as and when they come out. And we are able to also, because of the fabrics layer, we are also able to provide new transports as and when they emerge. So that those two layers are pretty well set. The other added benefit is we are able to have a common user interface for NVMe device management. We are able to persist connection. Once a user has configured all this information, we are able to persist it, and on reboot, reconnect all of them automatically. We have now the flexibility to go to our legacy stack, which is the traditional SCSI-based stack or the next-gen stack. And above all, actually, this simplifies the driver implementation significantly. Compared to that previous fat driver, the drivers can be very lean and transport specific. So those are some of the advantages. Here's a ladder diagram for the fabrics implementation. The top part of it is very ESX specific. I'm sorry, it's small. You need probably a microscope to see all this, but the north part of it is ESX native driver implementation specific, and the bottom part is standard NVMe specification implementation that we have. And this particular diagram actually shows the NVMe RDMA implementation. There's a slight difference, and I'll just cover that as I go along, expand on this slide. So if a user wants to configure a NVMe RDMA adapter, NVMe RDMA adapter is a software adapter. So the user has to go and request a creation of a software adapter. And as part of that flow, we will also have to specify which RDMA NIC that it needs to be bound with. That's on the leftmost side where we have the CLI, user-triggered action, which creates that software adapter. It registers a logical device in our native, in our device manager, which then walks it through the whole state machine of attaching and starting the adapter and scanning the adapter. This is all from a software driver perspective. Once the adapter is created and registered with our as a NVMe adapter, we kick off the NVMe protocol, NVMe commands specifically. We can, again, so the bottom part is, it's kind of generic and has common stuff which is shared between the fiber channel and RDMA and also for other transports. So once you have created the transport specific bindings, for example, once you have created the queue pairs for RDMA or the sockets for TCP, we are ready to start speaking NVMe. We can issue, in the case of fabrics, we are able to issue an identify command, get the remote targets information, enable the controllers. Once the controller information is available, we are able to go and create the number of queues and start the actual IO transfer. I had mentioned that there's slight difference in the case of fiber channel. So while RDMA requires you to create a software adapter, in the case of fiber channel, we are able to automatically do all the, because the fiber channel is based off of a PCI device, we are able to automatically create the VMHBA device, And also because of the discovery services that are available on the fiber channel side, we are able to discover and automatically log into the targets. So that's less pain for the administrator with respect to fiber channel. Here's an IO flow. How are we doing with the time?
Yeah, pretty.
It's okay. Here's an IO flow. And here again, the key is the command dispatcher. As you could have seen from the layered diagram, we are able to work both with the legacy SCSI-based storage stack as well as the next generation NVMe stack. And the command dispatcher is able to handle that kind of a muxing. Onto the south side, it's able to dispatch the commands to either NVMe PCI driver, encapsulated for RDMA or fiber channel. And essentially, in this model, we are able to have all of these transports up and running at the same time. Now I'm switching to just the UI workflows. This one is specifically for FC-NVMe. If a namespace service is configured, then, like I said, you don't need to do anything specific. You automatically detect, log in, and configure things. But in case it's not configured, we have an option in our UI to be able to go and specifically add a controller by providing the worldwide node names, etc., or even add specific controller as well. And once that information is provided, the UI will go ahead and present all the information of the various control, the devices it has detected, the namespaces that are behind that particular controller, as well as the controller information itself. So the previous one was the devices it detected, and this one is all the controller that's it's connected to. In the case of RDMA, like I had mentioned, you have to walk through the adding of a specific adapter. You specify which RNIC you want to bind to. Again, one of the other things I want to point out, the RDMA driver is agnostic. It can work on top of Rocky. We right now plan to support Rocky v2, but that same driver should be able to work on top of iWarp as well. And so once you've created, pointed it to the RNIC that you want to bind to, you can specify the remote target's IP address. You can discover the controllers behind that IP address and then log into the individual controllers that are behind that. And then present all the namespaces and LUNs which are sitting behind it. So we have a pretty rich UI which administrators will like to get all the operational information. We also have a very rich set of CLI, and ours is called ESXCLI. All of the commands that you do from the UI can be done from the ESXCLI as well. And the CLI is pretty self-explanatory. Once you log in, there's very detailed help, so you won't get lost. So that's NVMe Fabric. So now, as I had mentioned, once we have enabled the NVMe Fabric, how do you call it, the driver and the stack, there are very interesting use cases that are coming out. I mean, you probably heard from so many other folks of NVMe Fabrics being used for persistent memory use cases. And so there are a lot of interesting ones. A couple of proof of concepts that we've done with partners. This one is vSAN disaggregation with NVMe Fabrics over over Rocky. This was done with with Intel, where we showed how a vSAN cluster could expand its storage capacity over NVMe Fabrics onto their storage Intel storage system. This one was done with the RAF 1000 GSP JBOFs. This kind of shows how you can scale storage and compute independently. This was actually kind of the proof of concept was shown at VMworld a couple of years ago. On the similar vein, Lightbits did a proof of concept on ESX, again with vSAN disaggregation over TCP IP. The same benefits of how customer can scale. All right. In summary, NVMe Fabrics is here. It's really heralded very exciting times in storage industry. I can frankly say, like, over the period I've been in this industry, I haven't seen so much of interest in the ecosystem. Every partner would like to have a play in this. It's really exciting times. The standard is very promising. We can see the benefits. A lot of our other presenters have shown performance improvements benefits, which we can also realize. It's spurring a lot of innovation in the DAS and SAN models, and it's also pushing us OS vendors to provide the various transport of choices that customers need, right? And customers are the winners. So once they have it, they can have a blast. Thank you. That ends my presentation, and we are open for Q&A.
One question on the stack. Where exactly is the multipathing?
So yeah, the multipathing sits above the NVMe stack layer. What I didn't mention here is that we have something called a high performance multipath plugin, HPP. That was specifically used earlier for NVMe over PCI local storage alone. But we will be enabling that HPP multipath plugin by default for NVMe fabrics as well. And so we are able to do multipathing. We can handle path failovers and all that.
So that will work for direct PCIe NVMe attached devices also?
So yes, it was initially intended for design. Actually, it was released back in 6.7, vSphere 6.7. It was for use with NVMe local storage, but now we're going to make it available.
For dual-ported NVMe drives, if they were to be.
Yes, that discussion again as to support of dual-ported, I'm not exactly sure, but I've heard about discussions around that front. So. Yeah. Yes. Yes. So one of the requirements that we have from our target vendors that we have been working with is the need for a fuse command. So without that, we can't really do, because our VMFS file system requires that you have persisted locks on access to it from host. So we are, any of the target partners that we are working with, this is one of our, we have a questionnaire. So one of the asks is for them to support fuse.
So the ATS will get replaced with.
Yeah, that's right.
Are there any performance advantages in ESX? I know he showed other, it looked like Windows Linux charts.
Yeah, so we are, so again, this is work in progress. We are gathering performance information. We have realized, and I have not shared it because it's early for us because we still have some more runway to optimize stuff. But we have realized performance improvements, just like Jay mentioned, on the SCSI-based fiber channel versus the FC-NVMe. We are realizing anywhere from 50% to 200%, depending on the I/O block size being used and the queue depths. So we can see that kind of an improvement happening in between the protocols itself. With respect to RDMA, we have not really compared it against any other RDMA based, but we can, against like iSCSI and others, we are seeing very good improvement. All right. I don't know how much time was left. I rushed through it.
Just 5 minutes.
Going back to the hardware implementations, the NVMe promises as many, and you talked about thousands of lanes, thousands of entries in the queue depth, but you were going back to the physical implementations, the cores and ports. What is the largest implementation expanding out those lanes right now? Is it still virtually 64,000, or what is actually an implementation?
See, 64,000 is a standard, but I don't think anybody supports. So I've seen from 1,000 to 4,000 range. Yeah. Can you repeat your question? I couldn't hear it.
So disk-based replication needs to have an 85 channel. With this offering, I think eventually
So you're talking about services that run on top of this.
Yes.
Yeah, so those have to come right now. That I'm sure there are a lot of target vendors who are working on it. I've seen cases where they use this for some kind of high performance use case. They move the data over here because one advantage is you don't have to move it out of the network, right? If you have a fiber channel NVMe, you don't have to go through the process of moving it into something to do some big data processing or something like that. So they'd like to keep it in here and then process it and get the benefit with FC-NVMe.
Would that be an opportunity for embedded compute inside the storage devices themselves so that they could communicate across the I/O bus closely?
Possible, yeah. A lot of things are possible, yeah.
All right.
All
There are
right.
no more questions. Thank you so much for attending.
Thank you.